Then let's talk a little bit more in detail about pixel tracking. So, okay, let's move this thing a little. The main idea with pixel tracking is that you want to look how images change through time. And this can be any kind of image. It's really helpful and makes things a lot easier if your frame is fixed. If you have a satellite that's going and it takes the same place every day or every week, so you know that you can compare these images directly. Or if you have, like we have, these fixed camera setups that aren't moving. So you know that you're always taking a picture of the same place. So when this changes, it's not because your camera's moving around, it's because something happened in the environment. And this is used in all sorts of different applications. So for example, this is a landslide example where you have here at the beginning maybe a small start to a landslide, and then there was a really big landslide that came and blocked this river. And if you look at the difference between these two images, you can see the parts that were changing, right? And so this is from a paper that was looking at landslide detection, and they're just doing simple change detection on the images and saying, yes, this piece was probably a landslide, and maybe we should go look at it, or put out an alert that this remote area had a landslide. And there's lots and lots of different algorithms for doing this, depending on what kind of data you're using. If you're looking at glaciers that move quite fast versus a really slow landslide, you want to use different kinds of data and different algorithms to be able to deal with these different contexts. But the main thing you want to know is what is happening, what's moving within my images. The way that you can really think about this in terms of moving images, so in terms of videos, something like that, is that if you take one location, for example, this blue box, and then you go to the next time step, and you try to find, where is this thing in my blue box? Where is my orange landslide area? Has it moved to the right? Has it moved to the left? Let's try to match the content of this box to the location in this image. And if we see that this zone is now a little bit further this way and a little bit further this way, we know that there was some movement. And based on how many pixels each box has moved, we can figure out how fast it is. And maybe if I look up in this corner, right, this corner hasn't changed. Right, I have 3 here and then this blue shape. Nothing's changed there. So this would give me a velocity of 0. Nothing has changed. But if I go here, my landslide area now is, here it's 3 away from the bottom, and here it's 2 away from the bottom. So it's shifted this way. Most of these algorithms work in this kind of box window. So you find a box here, and then you check the next box, you check the next box, you check the next box, because it's really hard to work with the entire grid at the same time. So for computing speed reasons, and also just to make the statistics a little bit easier. So you can have some parts that don't move and some parts that do move. What this really boils down to is that you have certain blocks that you're looking at that are moving one way or the other. This is from one of these machine learning intros talking about this computer vision and tracking movement. So movement of a person moving one way or the other. This is exactly the same thing that they do in these autonomous cars, or if you have a self-driving car, or just when you have like a new car that has this automatic braking and things like this, when you get too close to some other car. They're taking these images. This is the first frame, and this is the frame after 1 second later, or half of a second later, whatever their speed is. And so they look, what's changed in my X direction? What's changed in my Y direction? So this car has moved this way a little bit, and this car has moved down a little bit. If you turn that together, or you put those vectors together, you get the velocity and which direction. And you don't get any changes in, for example, the road that's not moving. So this is exactly the kind of algorithm that they use for this kind of self-driving cars. This is also something that we use in, for example, glaciers. So if you take the difference between glacier images over certain periods of time, and you say, okay, there was this big boulder on my glacier in March, and now it's this way a little bit, it's come further down. If I check the location and the distance between them, I know the velocity of the glacier at different times. And so there's this, this glacier velocity service that you can go in and you can look at the velocity of any part of the glacier. And that's based on the same kind of pixel tracking, that you can get some velocity in your glacier through time. And of course, back to this same video, if you think about our little blocks here, right? We have a block in the middle, and where's that block going? And that's how we're going to track this. I think, yeah. So the main requirements that we need are that the camera is fixed. This makes things a lot easier. This is not what they do with a car, right? A car is driving while also checking. So that's part of why it's a little bit more complicated. But for us, we can have fixed cameras. We need to capture lots of images or videos. If we have images every 10 minutes and everything is changed, then we can't really tell the differences, right? And we also have to have some sort of texture. So we have to have some bubbles or different things in the water that we can actually differentiate. So the end goal then is to take a short video and try to figure out how fast the water is moving and try to test a couple of different algorithms for this. And I think that's it. Do you guys have any initial? So back to Python for a little bit now, and then we'll try to go through this and load in the video data and go from there. So the first thing I'm doing here, it's just like we did this morning, is I'm importing some different modules or packages. The matplotlib package is for plotting images, and this patches is for making arrows. So when we display velocity data, we often have some arrow, and this patches gives us these arrow charts. When we have velocity, we know not just the speed, but also the direction. So we want to be able to plot both of those things on top of our video, so we see what the direction looks like. So if I run this, and the last one, NumPy, this is this numerical Python, which we looked at before for having all the math functions. And datetime is just for dealing with timestamps. So when we want to plot our velocities through time, for example. The second little box here, this CV2, this is the main open source computer vision library. So computer vision is everything from machine learning to this kind of pixel tracking, any image operations you might want to do. All of these sort of AI models that can tell you if there's a cat in your picture or if it's a dog in your picture, these kinds of things, they're all trained with OpenCV. So the same kind of module used for these kind of tasks. Let's see if I can run these. This is where we test if my internet is still running. Now I check my import here. Okay, fixed. So when you run these two lines, this is just importing these libraries. So now we have these libraries available. We can use all of the different tools from these packages. And here I'm just defining a new variable that says my video file. So not the video itself, but just where it's located. It's called here video data and then the file name. So that's exactly the file that we're going to work with. The next thing I want to do is then try to open that and open it up with our OpenCV library and look at one of the images. So going back to our basic Python introduction, for those of you who are not so familiar, one more new thing to learn besides the lists and the data types is that you can define your own function. So if I write this def define, this means I'm defining a function that I can use for any of my images. And in this function, I want to take in some file name and make a plot. So I use my matplotlib. So this is exactly this Yeah, maybe I zoom in also. This is better. So my matplotlib library here gives me this PLT. And that's what I'm using here to make a new figure. So that'll open up a figure and pop it up on the screen. Then I'm using my OpenCV2 library. So this is my CV2 library that I imported here to read in a color image. And all this extra stuff is just how you have to tell OpenCV to work. OpenCV is not the most user-friendly library you'll ever have, but you don't have to worry about that because everything you need to know is here in this little module. And then I'm using my matplotlib again to IM show an image with a CMap, so a color map, and I define whatever color map I want. I give my plot a title, and I show my plot. So when I then go down here, and I use from the OpenCV library, the video capture function. That means I can give in a video file, and it will load it into a format that OpenCV now knows how to work with. You can't just say open. It's like this encoded file, right? Sometimes you get a video file and you can't open it on your computer because it's not in the right format. So OpenCV has to know that I'm trying to give it a video. And so this is why I use this video capture file. Once I've opened this file with OpenCV, so it knows what it's doing, I can read the first frame. So I use this .read function from my open file, and I can take this first frame and give it to my plot. So then I give this thing, and it will make the plot. So if I run this, it should just take a second. And this is the first frame from our video. So this should look exactly like the first one that I was showing in the presentation there. This is the first 1 second of our image, the first thing that we have. Working for everyone? No? Okay. Bodo, you want to? Yeah. Over here. So once we have one image, we can also get two images, right? So this is now defining a different function, get neighboring frames. So getting two frames that are next to each other. What it does is the exact same line that we did before, opening up the video file. It reads one file, and then it skips, so it uses one of these for loops to read a bunch of frames and discard them. It reads 100 frames, so maybe 10 seconds, or let's see, 3 seconds, right? 30 seconds per, or 30 frames per second. So if I skip 100 frames, I'm skipping about 3 seconds, and I'm getting my frame 1, which was my first frame, and my frame 2 is just a few seconds later, and it's returning me these two values. So it's giving me frame 1 and frame 2. So if I give in my video file, I can get frame A and frame B. One frame and then one frame 3 seconds later. And now I can put them together by using one NumPy command, which is hstack, horizontal stack. Put them right next to each other. And then I do the same show image command that we defined before. And that should just make me a plot. And this is all assuming that my internet is still running here, which it seems to be. Okay, it was still running, it was just slow. So now I have side by side 2 frames, right? And this is the kind of comparison I want to do. If I look, there's some places that are a little different. Here and here are a bit different. Some places are also quite similar. So those would have low velocities. This is what we want to do. Now, when we do these kind of computer vision questions, or these kind of pixel tracking things, there is a lot of images, or a lot of data in these images, right? We have all this color data, we have 1,000 pixels by 3,000 pixels, we have a ton of data here. So to speed things up, often what you do with computer vision is you turn everything into a grayscale. So you turn all the red, green, and blue data into just black and white. You turn it into an intensity value. To change this from a color image to a gray image, we can again use one of these tools in our OpenCV library, which converts color to gray. And all this will do is take 2 frames. So for example, my frames that I just picked here, and give them back to me as grayscale. So I'm pre-processing my frames. This function I define right here, which takes 2 images, and gives me back the 2 gray images. I'm stacking them together, just like we did here, and I'm plotting them with a gray color map. So this is, again, this same exact show image function that we had before. So if I run this, this should give me the same image as up here, just gray, right? So now I have these 2 images that have a lot less information for our algorithm to deal with. It's much easier to look at changes in just black and white images than in the red, green, and blue. So we're compressing our data a little bit. Okay, I'm going to continue, since it seems like most people have gotten this to run on Google Colab at least. I'm still working from this one because it runs a little bit faster, but either one, the code should run the same thing. So the idea with the grayscale is that we reduce the complexity of our math. When you do this kind of pixel tracking, it comes down to a matrix versus a matrix, right? We have one block versus another block. And if your matrix is just 5 by 5 and 25 values compared to another 25 values, that's pretty easy. If you have red, green, blue, color intensity, whatever, then you end up having this 5 by 5 by 5 matrix, so 200 and something values to compare again. So you're increasing complexity by orders of magnitude when you try to use color data. So we want to use the grayscale data because it goes a lot faster. We'll make our running this a lot faster. So even if this looks pretty similar to us, there's enough differences in there that the computer will be able to figure out what has changed and where it's changed. So one of the most commonly used algorithms and one of the faster algorithms is called the Farnabach algorithm, which you can see there's this nice link here that I put in the materials here that has this thing about optical flow. So it's basically trying to track movement as things move throughout the image. And this algorithm is from quite a long time ago, and it's used in quite a lot of different applications. This is, thankfully, not something that we have to think about the math ourselves and write this whole algorithm ourselves. We can do this calculate flow definition, which is directly coming from OpenCV. So OpenCV has a nice calculate optical flow Farnabach, which you only have to give it 2 frames. So for example, my time 0 and my time 1. And then these are some other parameters about how much movement you expect in the direction and things like this. That unless you want to get really fancy, you don't have to tweak those. So these are the sort of default values that I took from this tutorial. This is the easiest way to run this algorithm. What we end up with from this is this flow matrix. And that gives us the direction in X and the direction in Y. So if we know that it's going really fast in X and really slow in Y, we can calculate the total direction and also the angle. So those are the 2 things that we really need, right? This dx and dy that turns us into a velocity. And then this second, slightly longer definition here is just about visualizing that data. So this data will take our nice flow format, so our dx and our dy grid, and downsample it a little bit. We don't need every single point to have an arrow on top of it. So this command is taking some step size, so in this case 16, and so every 16 pixels it makes an arrow. That's all this is doing. It's taking every step size and splitting our data down, making it a little bit smaller, and giving us back our y and our x, which we can then use to make our plot. So when we make a quicker plot, first we're using the same image show that we used for our raw data. So we put our raw first image on there, and then on top of that, we want to use this matplotlib quiver. And that is then how we plot these arrows. It takes the start of the arrow and how long the arrow is. And then, so the x and the y location of the start of the arrow, and then how long the arrow is in the x and the y direction, some color, and other sort of scaling things that you also don't have to worry about so much. If I run this, I'm just going to run this on 2 images. So just the difference from 1 until 3 seconds later. And then I'm going to plot this data, so I get this raw flow. I give it my initial image to put as the background, and then I put my arrows on top showing the movement that it calculates. So hopefully this will run. It should just take a second, as long as my internet connection stayed. Yes, good. And what it gives us is something that looks like this. And you can see that it's finding most of the motion here along the edges, where it's going really fast, right? As it goes up and over this drop in the river, that's where we get these really big vectors of water movement. We also get some exactly in this sort of lighter patch that I pointed out before that was changing a lot. There we also get good vectors. But most of this, it's quite small, right? These are really, really small vectors. It's not moving that much. Some of that is just the units, and some of that is that these arrows are off because of this piece of grass that's going really fast back and forth, right? So this is kind of noise that we want to get rid of from our image, something that we don't really want to work with. We can do 2 things to try to deal with this noise. We can try to find out where exactly there's these noisy parts and remove them and then rerun our algorithm, which is really tough. First, we'd have to identify exactly where there was grass and where there was water. Or we can say, we're only interested in this box in the middle. So let's just clip out this box and we ignore everything else. If you know that some part of your image, like over here, is always on the bank, it's never water, you can ignore that. You don't need to spend computation time calculating velocities on some rocks that are just sitting there, right? So that's what I'm doing in the next step. I'm first going to rotate my images, right? This is a little bit funny looking sideways, so I'm going to rotate it back up so we look in the same view of the camera. So I'm rotating it 90 degrees clockwise, or counterclockwise, so back that way. And then I'm subsetting my image. Since this is a NumPy array, think of it as a big grid of x values and y values, I can say I want all of my x values. So I use this colon. And then all of my y values. So this colon means give me everything in the first direction. And in the second direction, I want to go from point number 800 to point negative 400. So I can reference from 0 until the end. The end is -1. And say I only want to keep this subset. So this is going to give me back the image, but clipped a little bit smaller. And now I get my rotated data, sort of my original data and my full rotated data. And if I look at those, I can see what the subset image looks like. Now, I've centered my image right here in this sort of middle part, and I've rotated it this way, right? So this is this point where it falls over the water and goes faster. There's still a little end of this piece of grass here, but it's no longer right in front, the main problem. And we're right sort of towards the end of the bank here, so we cut a little bit off there as well. You can change those numbers and focus it even more to the middle if you want it to go faster, but this gives us at least a view of the main part of the river that we're interested in. So if we use that subset, I click yes. If we use that subset, so for example, I take my image 1 and my image 3 seconds later, and I subset them, and I calculate my flow, just like we did before. And now I have one new function in the middle here, which I'm filtering low magnitudes. So I want to get rid of all those really, really low pixels. So mask out stuff that's on the land, or boulders that aren't moving, these kind of things. So to do that, I have this arch to polar function, which turns my flow into these arrows. And I find their magnitude, and I say I want to move, I have some velocity magnitude that I want to threshold with, and then I just set all of that mass data to 0. Now I'll get back the same set of arrows, but anything that was 1 or 2 gets set to 0. And anything that's bigger than that keeps its real value. So this is just a way to mask out some of the unnecessary data. And hopefully that runs a little bit faster since we're looking at a smaller area. And we can see that now we've gotten rid of some of our grass problems. We still have the most velocity here on these edges, but we've gotten rid of some of the data that we don't need to deal with. So all of this stuff up here is zeros. It's a little bit hard to tell with these arrows, but trust me, it is. The other thing that you often do in something like a river, well, you know that water should go in a similar direction, right? If water is going down the middle of the stream, it's all sort of going the same direction. So if you have some water that's going backwards, but the rest of it nearby is going forwards, you can check. In my neighborhood, if 95% of the data is going to the right, and I have one point going to the left, that point to the left is probably an error, right? And based on that spatial consistency, or how consistent those directions are, I can also remove some outliers. So that's what this other function here, this is also all written in here. Filter spatial consistency. I do my grid subsetting the same as I did before. I turn my arrows into these magnitudes and directions, and then I check the angle. And the way I do that is I look through the whole grid and say, in this box of 8 by 8 or 16 by 16, are all the arrows going in the same direction, or are all the arrows going in different directions? And based on that, I can know how consistent my data is and how reliable it is in different parts of the image. So if I run this, this should now filter out some more stuff, and hopefully that gives us some filtered flow. So now I have these arrows that are a little bit more bunched, going in similar directions. Some of the ones that were sort of going like this and this are now gone. So if I have a big bunch that's all going down, that's the direction that I trust is the real direction of my river. So far, we've only been working with 2 frames, right? One image, and then one image 3 seconds later. But we have an entire video, right? We have 30 seconds of video or 10 seconds of video, however much. Which means that we can get a more accurate view of the velocity if we average all of these things. So we check for each pair of images, what is the expected direction? And if we average all of those things, some of this noise will disappear, and we'll get a more accurate view of what the actual river velocity is over this whole time period. So the first thing I want to know is roughly how long my image or how long my video is. It gets really, really expensive. You saw it took maybe 10 seconds to do this for 1 frame. So if you have to do this for 10,000 frames, you're going to be waiting for a very long time. So this little function here just checks, says, okay, here's my frame 0, and then checks, is there still another frame? Can I read this? If there's no more frame, break me out and tell me how many frames I had left. If I run this, this should give me a count of how many frames I have in my video. And that gives us an idea of how many images we're working with here. So I have 893 different images. If you want to run only 100 images, you're still going to get a pretty good average. If you want to run 500, you get maybe a little bit more accurate. Above that, you don't really need to run that many more frames. T is coming. Okay, then that's a good place to start the recording again. So there's a lot of different ways you can do this. I made one really long function that does all of this for us, so I'm going to go through a little bit what is actually happening. So this new calculate median flow is going to take our flow vectors for hundreds of images and get the median, so figure out what direction they're going in and how fast. And inside of this, I have this same subsetting function we had before, right, that just clips our image to the middle part, so we focus only on the middle. And it first gets one frame, converts it to grayscale, and then makes an empty list. So just like we talked about this morning, we have these Python lists where we can store lots of different things in them, right? And the other thing I want to store every time is the count. So I start with 0 frames. Every time I add a new frame, add a new velocity, I increase the count. And the reason I do that is because maybe I only want to check 100 frames, because that will be much faster than checking 900 frames. So in my function, I have this maximum frames variable. And that lets me tell the function to stop after a certain amount of time. I can also do some subsampling. And that just means skip 5 images every time. So don't look at 1 and then 1 millisecond later, the changes are too small. Check at least 5 milliseconds later, or 5 frames later. You can put this to 10 frames, however you want to do it. So, once I've set up all of these different things, it's going to tell me I'm going to process some amount of frames and keep one every 5, for example, using this subsample rate. Keep 1 frame every 10. I don't need a median for every single frame. And then we'll go through and first check, did I already check too many frames? If so, I'm going to stop and just give back my median. Otherwise, it's going to read the next frame, convert it to grayscale, subset it, calculate our optical flow, and if we're below our subsample rate, so if we're at the 5th image, or the 10th image, or the 15th image, we're going to add this to our list. So we're going to store our flow into this big list. Now our list is then going to contain a few hundred of these different flow grids. And every time I store something, I increase my flow count, so I know how many frames I've processed. At the end, I stack them all together and compute the median. And what you get back at the end is just this median. And of course the first image, so we have something to plot on top. So if I run this, I can get back my flow vectors. I can check them for this spatial consistency again, like we did before. And I can print, or I can make this map with my final frame and my final filtered result. And we're going to see what the time aggregated plot looks like. Now I've zoomed too far out, I can't see this. There we go. Now, this is going to tell me as I keep processing. I set my frames to 250 just because I don't want to sit here for 20 minutes while this runs. It's going to take a little bit of time. I have no idea how long this will take on Google Colab, since Google Colab is a little bit slower than the computer that I'm running on. So now it's printing out some data. See, I have here in this, let me move this out of the way. I have in here, if my frame count is divisible by 100, print out how many frames you processed. So it's just giving me a progress bar, so I know roughly how many frames have been processed. And at some point, it'll tell me I finished checking all my frames, and it's going to compute the median, and then it's going to make my flow vector. And now this looks a bit different, right? It's smoothed out quite a lot of this noise, partially because right here at this sort of where the different types of water meet, it's quite chaotic. Some frames, it's going straight up, some it's going down, some it's going sideways. It's sort of like a whirlpool, right? And if you average all of that together, you end up with a much smaller vector. You add all the ones going left, all the ones going right, and you end up with 0. We can make this a little bit clearer by scaling the vectors and also giving them a little bit of color. So right now the vectors, since they're an average, they're a lot smaller. So if we want to scale them to be something a little bit bigger so we can see these small bits of movement, we can change our function just a little bit. This is based on exactly the same visualization we did, except it's now, I called it enhanced. So this is going to give me a scale factor and some maximum speed, and it will also add a color map. So my arrows will also be colored by how fast they're moving. So this is just can help visualize this a little bit better, and hopefully this goes relatively quick. I put some notes in here so that the quiver plotting is a little bit funny. If you put a small scale factor, it makes them bigger. It does this inverse distance when it does this plotting. And the color map I also defined as plasma. So we have the blue parts would be the slow parts, and the yellow parts should be the fast parts. And I will also now add a color bar, since this now my plot will have also some colors on it. So I put a color bar so you can see what the colors mean. And that took a second to plot with all the colors. But now we have something that you can see more like a heat map, right? And we can see that we have these longer, faster patches, especially here where we're flowing over the different parts of the river. But also here along the banks, right? These are a little bit faster. And we still have this slower part in the middle of the river. If we're most interested in this flow sort of in the middle, the main part of the flow, rather than this sort of chaotic stuff on the edges, we can also mask out some of these really big ones. Instead of using my default max speed of 100 pixels, I can do something much smaller. So I can make my maximum speed rather 0.25 pixels. Now the units of this speed are a little bit tricky since we'd have to convert it from pixels to actual distance units based on how far the camera is from the water. But for our visualization purposes, if we pick a smaller speed and a bigger scaling factor, we can see the slower parts of the river pretty well. This will again take a second to visualize here, but then we should be able to see the slower parts of the river. There we go. So now we've masked out some of the really, really fast parts, especially here along this edge, right? And on these faster parts along the edge. And now we see that even though it looked quite still in here, right? We still have movement, and it's basically all going in this direction, right? So it's all going in exactly the direction we expect our flow to go in. And if you wanted to, focus in on this sort of more stable part and pick this out, that would be a good place to get the average flow speed of the river, ignoring these churning parts around the boulders. Now, we've done this for one video, but if you have a video every hour, you can take out this piece, get the average, and then you could make such a line chart through time and see if it's going faster or slower throughout the year or throughout the day. That's the main idea of using such an algorithm. Yeah, so that's the intro to this pixel tracking. Are there any questions now that we've done these extra visualizations?